Let's see these relationships graphically also. And what I will do now is that I will plot, for example, S versus T. So displacement can be plotted as a function of time, and obviously that displacement will be rectilinear motion, so that displacement will be only along one line, either rightward or leftward, right? I can also plot velocity versus time, so we will also see how the what conclusion or one insight we can obtain from a relationship between velocity and time. Similarly, acceleration versus time, right? All three parameters, displacement, velocity, acceleration versus time. And then we will also be like plotting A versus V or A versus S also, right? But first, see these three basic graphical relationships, right? The very first thing you should keep in mind, for example, let's first start with S versus T, the position coordinate versus time. So if I give you this relationship graphically, which looks like this, right, like this, S versus time, like 0 second and let's say some 10 seconds, right, and S is, for example, some 10 meters. It is very important that you make a picture of that motion in your mind also, even before starting to solve the problem, right? Picture of that motion will actually mean that now the motion can only occur along one line, and let's assume that I am the origin and the motion can only occur along this line and I am in the middle of that line, right? Towards my right is the positive displacement, towards my left is the negative displacement. So this is the positive x-axis, like the upward axis, and it could also be negative, but currently the line is only like this, right? It linearly increase and then suddenly come back to the x-axis, which is the time axis. How that motion would physically look like, yes please. Yeah, for example, a ball which started from the point where I am standing now, which is origin, and then move towards my right because the motion is positive, right? Linearly move towards right, and then after reaching to 10 meters, suddenly come back to me again, right? So from this point, it suddenly come back, drop to point where S was 0, which means the x-axis, right? So the motion was like displacement started increasing in time, reached linearly to 10 meters and drop to 0 again, right? Imagine another relationship between S and T which graphically looks like this, right? How that motion would look like. That particle start from my position, move towards my right gently, right? And then for one particular moment it stopped there and then reverse its direction and come back to me again gently, right? So the displacement start increasing in time, reach to its peak value, let's say 10 meters, and then start decreasing again, which means that particle is now again coming back to me, and then after certain time it just come to origin again, right? Another, for example, graph which may be like this, right, like this. So now the particle is moving towards right gently and then coming back to me, and then also going towards left and then again coming back to me. So it's like kind of moving to and fro about the origin, which is my location, right? But this motion is all in one line, right? So it's no curvilinear motion, it's just like to and fro motion in one line, right? So all of you can make a picture of that motion, right? So it's a fun exercise that you just plot any graph and then imagine how that particle's motion would look like. For example, what about this kind of a motion, like this? Particle moved from origin, suddenly go to right within no time, suddenly come back to me and then suddenly go to the other side, right? So like it's start from origin and within no time it reach to some distance towards right, and then it stays there for certain time and then suddenly come back and from right to suddenly go to the left side, stays there for certain time, and then again keep on repeating that, right? Imagine another graph like this. So now it's not like very sudden, but like fast movement towards right, then fast movement towards left, but without any stop, because now exactly as the time it reached to peak, at the same time it changed its direction, and the displacement start reducing, and then displacement become negative, then again it start increasing, become positive. So it's like sudden movements towards right and towards left about the origin, which is like my location, right? So another S versus T graph. Let's have one or two more. For example, like a graph which look like this. Like within no time it reached to a very high distance, then within no time it come back and then just stays with me, right? So S versus T can look like an exponential up or exponential down also. All of these figures which I am drawing have mathematical functions describing them, right? So for example, this is a linear function. This may be a parabolic function. This may be a sine function like trigonometric function, right? This may be an exponential or logarithmic function. These two, for example, at the bottom, they are periodic functions, which means which are generally described by piecewise function. Piecewise functions, like a function which is describing the motion for a particular time in duration, and then same pattern is being repeated again and again. These kind of functions are called periodic functions, generally described by piecewise equations. So you describe the equation for one cycle, and then you say that it repeats the same for all number of cycles, right? So just now do that exercise whenever you are free, that how the motion which is like this will look like, right? You can even represent any dance of a particular particle with this graphical notation, right? S versus T graph will give you many other information also, and one of the most important one is, for example, let's first consider a simple case that S versus T relationship is graphically represented by this red line. So this is S versus T, right? So we now will apply two basic concepts of calculus. Let me just quickly state them, and then we will apply to all three relationships, S versus T, V versus T, and A versus T, to see what conclusion or insight we can get about the motion. So the first basic principle you know already from calculus is that whenever you have a function f of x, let's say that x is the independent variable, y is the dependent variable, which is plotted as a function of x, right? So let's say that is that function, graphically look like with this line. We know that at any particular value of x, we can take the tangent of that curve, and the slope of that tangent will be the first derivative of that function with respect to independent variable, right? So if this is the tangent at a particular x, right, then the slope of this line, this tangent, generally the slope is represented by a small triangle with base length equal to 1, and then the vertical height is actually the slope, right? So this is the slope of y, which is f of x, and that slope mathematically is the first derivative of y with respect to x, right? And we can also write it as d of f of x with respect to x, right? That is the first information which you can recall from basic calculus, that whenever a function is plotted, you can take the slope at any particular value of independent variable, and that slope of that tangent will represent mathematically as the first derivative of that particular function with respect to independent variable, in this case derivative of y with respect to x. The second concept which you can recall from basic calculus is, for example, again the same case, y is equal to f of x is plotted on y-axis against the independent variable x, and you have that graph. If you have two certain values of x, for example x1 and x2, the area enclosed by that function between x1 and x2 is mathematically equal to the integral of that function with respect to x, right? So this shaded area which I am shading now is the area enclosed by that function graphically between two certain values of x, x1 and x2, is equal to, this area is equal to a definite integral from x1 to x2 of that function which is actually y or f of x with respect to x. So you take that integration with respect to x for that function which is actually equal to y here, right? And that integration, definite integral, will actually be graphically equal to the area enclosed or shaded area here in this figure, right? So all of you are familiar with both of these concepts, right? So let's quickly apply them to our acceleration, velocity, displacement to get some insight about these relationships. So first graph was the displacement versus time, and if we take the tangent at a certain time t, and the slope of that certain tangent will actually be equal to the first derivative of y with respect to x, here in this case displacement with respect to time, right? So this line is tangent, right? And this first derivative is actually the slope of tangent, right? So it means that now if I give you the s versus t graph, you should be able to graphically determine the velocity also, right? One thing you can do is that I give you a function describing this red line, equation of that function, and then you differentiate it with respect to time to get velocity. But another kind of solution can be graphical solution, that I directly give you the graph like the data to plot red line, and then ask you to determine velocity at a particular time, which means I am graphically asking you to draw a tangent at that time and calculate its slope, right? So there is a graphical interpretation, and also there is a analytical interpretation in terms of derivatives and integrations, but there can be a graphical interpretation also. So at this particular time, if the graph is given, you can determine graphically, you can determine the velocity as the slope of that tangent. Tangent is defined as a line which is touching that particular function only at one particular value of x-axis, here in this case is particular time, right? Similarly, if we have the velocity versus time graph, right, and that red line is available to you, and at any particular time t, if you draw the tangent, so this is the tangent at any t, right, and then the slope of that tangent will be the first derivative of y with respect to x, which means velocity with respect to time, which means acceleration, right? So acceleration is graphically determined as the slope of the velocity time graph, right? So some quick observations you may also have from these graphical interpretations. For example, let's go back to this case. For example, if I give you s versus t graph which look like this, you know exactly that the slope will become 0 for a particular time instant, because here if you draw a tangent it will be exactly horizontal, which means having a 0 slope, and slope graphically is equal to velocity. So you know physically now that for a particular time instant the object will actually come to rest, and then its displacement will start reducing, right? So whatever the velocity versus time graph for this case is, you exactly know that it should pass through this t axis at that particular time step, that one, right? So it should be like something like this. Whatever velocity you have before that time instant or after that time instant will be non-zero, but at that time instant the derivative was 0 or the slope of tangent was 0, right? So some observations you may have graphically also without even doing calculations, right? Similarly, let's apply the second principle now to this figure V versus T. That for example, if you have any two time instants T1, T2, the integration of function, which is the actually velocity, from some value of velocity like V1 from V2, where V1 and V2 are the velocity values at T1 and T2. So if we integrate velocity, we should be able to get the net displacement, right? So that area enclosed between T1 and T2 is equal to this integral, graphically equal to this integral, but we know that integration of velocity is actually displacement. So that area should be equal to the net displacement between T1 and T2, right? So you can also determine graphically displacement if the V versus T graph is given, right? Obviously, in order to evaluate this integral, you may require the equation of this red line, right? But what if I give you like a rectangular line, like a line which is like this, and you can easily determine the area enclosed by that line by dividing it into triangles and rectangles, and then that area graphically should be equal to the net displacement which that particle covered between T1 and T2, right? So this is exactly the same relationship which you studied in last case or last slide, but now represented graphically. Similarly, the last graph, which is acceleration versus time, again let's apply the same principle, that if we take the integration of function which is on y-axis with respect to the function on x-axis, right, that should be equal to the area enclosed by that function between those two time instants. So for example, t1 to t2, integration of acceleration should be actually equal to the shaded area, this whole area, right? So this is shaded area, and integration of acceleration is equal to net velocity between t1 and t2, right? So it means that if I give you acceleration versus time relationship and ask you to determine velocity, one way to do is just integrate that, right? If the equation is available, but if the equation is not available and I directly give you this data to plot that graph, then you need to calculate the area enclosed between those two time instants in which I am asking the net velocity, right? So that will be the graphical way to solve the same problem, which we can also do analytically using integrals and differentiations. Now let's see two more graphs. Like we have already seen S versus T, we have seen V versus T, and similarly acceleration versus time. What if I give you the acceleration as a function of displacement, right? And that can be given in both ways. It can be given in the form of an equation, or it can also be given in graphical form, like I give you the data to plot that red line, right? So what will be the area enclosed between any two distances? What would that look like actually? For example, here the integration of y, which means a, with respect to s, which is s here, between any two distances like s1 to s2 will actually be graphically equal to this whole shaded area, right? Using the same calculus principle. So shaded area is actually the area enclosed by that function between those two values of independent variable, which is now distance s1 and s2. So we now know equation 3. Let's recall equation 3. What was ADS? ADS from equation 3 was VDV. Let's go back quickly to see what was equation 3. Actually 3A. ADS is actually VDV, right? So let's use that equation 3A and see what it will become. So here we have this integral, and we can write it as VDV, and now the limits will be from V1 to V2, where V1, V2 are defined as the velocities at T1 and T2, right? So we will be having this integral, and now the whole integral is in the same variable like velocity. Previously it was acceleration being integrated with respect to displacement, but now it's velocity being integrated with respect to velocity. So we can evaluate this part of the integral also, right? This will actually become v square over 2, and the limit will be from v1 to v2, and that will become actually 1 over 2 v2 square minus v1 square, right? So now the shaded area which I highlighted here is mathematically we determine that it is equal to 1 over 2 v2 square minus v1 square. That is a very useful relationship. If I ask you, if I give you acceleration as a function of displacement, we derived one quantity which is in the form of velocities, right? So we can relate between A, S and V now also, because this graph will give us something in terms of velocity also. Finally, if I give you A as a function of, V as a function of S. Now velocity is plotted as a function of displacement, and there is one interesting conclusion which you can draw from here, and let's say that that red line is representing the velocity displacement relationship. Now at any particular value of S, we know that let's represent that particular point A, and this is the tangent point, right? Tangent. Perpendicular to tangent is a line called normal. So this AB is normal, right? dV by ds will become the slope, because this is a Vs relationship. So whatever is the slope, that is the first derivative of y with respect to s, means dV by ds, right? So now let's see these two triangles. This small triangle, which is drawn just for the purpose of showing the tangent or the slope of tangent, and this triangle which is ACB, right? The triangle which is formed by the normal line, and this is the vertical line connecting A to a point C, and the height of that line will be the velocity, right? Because at any time instant y-axis is the velocity, so this AC is small v. So the length of AC is the velocity, right? And we will now prove, as you can see here also, that the length of CB will be mathematically equal to acceleration. And how? That small triangle and this ACB are actually similar triangles, right? How, for example, we can prove that all of their three angles are equal. This angle is 90 degree and this is also 90 degree. So their first angle is same. Similarly, let's call that small angle as theta, right? Now, you know that then this angle actually will be 90 minus theta, right? Because it is the total angle is 90 between tangent and normal, right? So that angle will be 90 minus theta. If that is the case, then that angle should also be 90 minus theta. How? Using alternate angles. For example, we know that if there are two parallel lines and there is a third line crossing them, then this angle should be equal to this angle, right? They are alternate angles. So this line, horizontal line which is passing through A is a horizontal line. Your s-axis is a horizontal line, right? And this AB is actually crossing these two horizontal lines, right? So 90 minus theta, this angle will be actually alternate to this angle. So these two should be equal, right? Everyone is clear? And then if two angles are equal, obviously the sum should be 180. So the third angle, this one, should be actually equal to that one, right? So all three angles of the small triangle and the big triangle are equal, which means they are similar triangles. And similar triangles, we have a rule, you know that already, and that rule is that if, for example, this is a small triangle, this is a big triangle, if this is A, B, and this is capital A and this is capital B, then you know that small a over small b should be equal to capital A over capital B, right? So the ratio of their side lengths should be equal. So we can do that with this small triangle and big triangle. So we can write that dv by ds will be this height divided by this length, which is 1, should be equal to CB over this V, right? So CB is this length and this is that length, right? So I simply equated the ratio of corresponding two sides for the small triangle to the large triangle, and this relationship will give me CB is equal to VD, this should be dV by ds, right? dV by ds. So CB will be equal to VdV by ds, right? And by equation 3 again, we know that ADS is equal to VdV. This is your equation 3, and from here you know that A is equal to VdV by ds. So this ratio is actually equal to the A. So we now prove that on the scale which was actually representing distance, right? So this was s-axis actually, distance axis. But if you mathematically determine the length between C and B graphically, right, that should be equal to acceleration, right? It doesn't mean that your quantity which is being described by x-axis is acceleration, but if you graphically determine the length by actually dropping that tangent and normal and doing that triangle exercise, if you determine CB length, that should be equal to your acceleration, right? This is one interesting graphical concept which you can derive by doing that exercise. So one last thing before we end, that last thing will help you in being an effective problem solver in tutorials. If I give you the displacement versus time relationship, either graphically or numerically or analytically, for example, I give you the equation, right, and ask you to determine velocity, you take its first derivative with respect to time. So if S versus T relationship is given, for example like this, a cubic equation in T is given, which can be plotted and get the curve. Analytically, you can take its first derivative like ds by dt to determine what we call as velocity, right? Velocity will be a second order polynomial, a quadratic equation. Velocity will become 6t square minus 24, right? If I ask you to plot acceleration or determine acceleration at a particular time, you take one more derivative and acceleration will become like 12t, that 12t, right? One more derivative with respect to time. And if I ask you to determine velocity at 3 seconds, put t equal to 3 seconds. If I ask you to determine acceleration at 5 seconds, put 5 seconds in this equation, right? So the forward differentiation is easier if I give you S versus T and ask you to calculate V and A. But you will find problems in your next tutorial in which I will give you acceleration and ask you to determine V and S, which means you need to integrate A in order to determine velocity and acceleration, and that integration will depend on in which form I give you acceleration, right? For example, if I give you acceleration as a function of time, like if I say acceleration is 3t cube plus 2t square plus 5, that is again easy because you have acceleration as a function of time, so you can simply integrate it as with respect to t and integrate it one more time to get displacement, right? So you can do it analytically and you can also do it graphically.